Welcome back to the deep dive. We're ripping open the sources you shared with us today, diving deep into some fascinating research and the topic. It's something super practical, impacting the flow of cities everywhere, urban mobility.
Exactly. Yeah, if you've ever been stuck waiting ages for a ride or, seen a bike share station completely full in one spot while another's totally empty nearby, you've felt those urban mobility inefficiencies firsthand.
And they're not just small annoyances, right? They add up to wasted fuel, more traffic, just generally frustrated people trying to get around.
Absolutely. It's a system-wide cost.
And fixing these kinds of problems, or, well, even just making a decent dent in them, really hinges on one critical thing: being able to accurately predict passenger demand. Not just overall demand, but like where people will need rides or bikes, and crucially, when.
Right. That prediction piece is key. But forecasting something as, well, dynamic as citywide movement is incredibly complex. The data involved isn't simple. It's fundamentally spatio-temporal.
Spatial temporal, meaning location and time are baked in together.
Exactly. Location influences demand over time, and time influences demand patterns across locations. They're tangled up in these really intricate ways.
It's definitely a knotty problem. We've seen attempts to untangle it before, of course. You're probably familiar with things like graph neural networks, GNNs, good for modeling connections between places.
Yeah, GNNs are useful for understanding the sort of fixed map of a city.
And the field has also, increasingly borrowed ideas from other areas like attention-based methods, inspired by successes in, say, language processing.
Attention has been powerful, yes. But as the sources you've shared really highlight, even these advanced methods, well, they still have significant limitations. They don't quite capture the full, messy, complex picture of urban demand.
Right, which perfectly sets the stage for our mission in this deep dive. We're going to unpack a specific research paper you sent over, along with your excellent notes and that briefing doc. It focuses on a new model designed to tackle these exact challenges. It's called ADFormer, and it seems to bring some genuinely novel ideas to the table for spatio-temporal forecasting.
That's the plan. We'll explore the academic contributions, the core ideas, but also the practical side, how it aims to get past those limitations we just mentioned.
Okay, great. Let's start by really digging into the problem itself. Why is forecasting demand in a city so, well, persistently tricky, even with all these fancy models?
Well, the core difficulty, as the paper lays it out, is precisely those interwoven spatio-temporal dependencies. It's just hard to model them fully. Predicting demand in, say, neighborhood A at 5 p.m. isn't just about what happened in A at 4 p.m. That's too simple.
Right, it's connected to lots of other things.
Exactly. It's influenced by what's happening right now in neighborhood B, maybe offices letting out there. It's influenced by patterns from hours or even days ago. Across many areas, think weekly commutes, weekend habits. And it's also tied to the fundamental character of neighborhood A itself. Is it residential, commercial, an entertainment hub, all that matters?
And the sources you provided, they do a good job pointing out where earlier methods fall short with this complexity. Let's take GNNs again. They work well when relationships are fixed, right? Defining A and B as connected. But in reality, the important connections for demand, they shift constantly. Time of day, special events, even the weather.
Precisely. How do you define one static graph for something so fluid? GNNs capture that fixed topology, yeah, but they struggle with the dynamic, ever-changing nature of how people actually move. The relevant connections aren't fixed.
Okay, so GNNs have limitations there. What about the attention-based methods? You said they're better at dynamic connections.
They are generally. They can learn to pay more attention to certain regions or time periods as needed. But even they, this paper argues, tend to suffer from two main problems.
Ah, okay, and this is where ADFormer starts to make its case, targeting these specific issues. The first one they mention is attention noise. What's that?
Yeah, attention noise. So think about how standard attention works. It tries to figure out how much influence each piece of input data should have on the final prediction for a specific place and time. Now, imagine applying that across hundreds, maybe thousands of different zones in a city.
Okay, lots of potential connections.
Exactly. And the reality is most of those potential connections are weak or irrelevant or just random statistical noise. The paper describes this as the model getting distracted, disproportionately focusing on irrelevant regions.
So instead of locking onto the few really important signals,
Its attention gets spread thin. It becomes weak and dispersed across lots of areas, rather than being sharp and focused on what truly matters. The paper has a figure, figure 1A, that starts to show this visually like a fuzzy, weak map of connections.
Okay, so it's like trying to listen to one person in a really crowded, noisy room. The model hears bits from everywhere, can't quite focus.
That's a perfect analogy. The noise drowns out the important signal. And the second major limitation they point out is what they call the neglect of high-level correlations. This is really crucial, according to the paper.
High-level correlations. What does that mean for city demand? It sounds like seeing the bigger picture.
Pretty much. It means demand patterns aren't just driven by what's happening right next door, or simple one-to-one links between areas. There are broader patterns, structural patterns, that emerge across the city based on how areas function, even if they're miles apart.
Ah, okay. Like two residential neighborhoods on opposite sides of the city might have similar morning rush patterns?
Exactly. Or two downtown business districts might peak around lunchtime. Even if they're geographically distant, their functional role makes their demand patterns similar. Figure 1B and 1C in the paper illustrate this really well. They show these conceptual clusters of regions, residential clusters, commercial clusters, and so on. And the key insight is regions in the same functional cluster often show remarkably similar demand curves over time, while having very different patterns from regions in other clusters, even nearby ones.
Okay, so existing methods focusing maybe too much on nearby connections or direct links, they might miss this functional similarity.
That's the argument. They often overlook these crucial higher-level spatial patterns, maybe temporal ones too, that are driven by function, not just pure proximity.
So to really nail this, you need a model that can do two things. One, filter out that noisy chatter at the fine-grained level, and two, explicitly recognize and use these broader functional patterns linking areas or times that behave alike no matter where they are.
Precisely. And that's the core philosophy driving ADFormer. It's explicitly designed to hit both those points. It introduces new ways to reduce that attention noise, especially spatially where you have lots of regions, and it has specific components to capture those high-level spatio-temporal correlations.
Okay, this is exciting. Let's unpack these innovations. How does it clean up that noisy spatial picture first? They call it spatial differential attention.
Yes, spatial differential attention, or SDA, that's one of the key academic contributions highlighted in the paper. The reason it's needed, like we said, is that applying standard attention across potentially hundreds of city regions is just asking for noise. Most connections are just not that important for a specific prediction.
Right, and the way it works is pretty clever, borrowing ideas from other fields.
Yeah, it's inspired by some techniques used in like large language models. The core idea is to get a cleaner signal by comparing two different VGs of the attention, instead of calculating just one big matrix showing how much each region attends to every other region.
It calculates two.
It calculates two separate attention score matrices. Then it literally takes the difference between them. The idea is that this differencing helps cancel out the common, noisy baseline connections that appear in both views, while amplifying the connections that are strong or unique in one view compared to the other.
Ah, so it highlights the differences, which are more likely to be the meaningful signals.
Exactly. It helps denoise the scores, letting the model selectively amplify the most informative correlations while suppressing noise, as the paper puts it. It sharpens the model's spatial focus.
Okay, cool. So SDA tackles the noise at the individual region level. But what about seeing that bigger spatial picture, those functional clusters you mentioned? How does ADFormer capture those?
That brings us to the second spatial innovation, the Spatial Cluster Attention, or SCA module. This part is specifically designed to capture those high-level spatial correlations based on function. The core idea is simple. Stop looking only at individual regions. Look at groups or spatial clusters of regions that behave similarly.
And how does it figure out which regions belong together? Is it just geography again, grouping nearby areas?
No, and this is another key point the paper makes. It's not based on geographical proximity. It's based on the similarity of their historical demand patterns.
Okay, how does it measure that similarity?
They use an algorithm called dynamic time warping, or DTW.
ETW, I've heard of that. It's used for comparing sequences like time series, even if they're a bit stretched or compressed.
Exactly. DTW is really good at finding how similar the overall shape of two time series is, even if peaks or valleys don't line up perfectly in time. So they use DTW to compare the historical demand data between pairs of regions. Regions whose demand patterns have similar shapes over time get grouped together.
Regardless of whether they're neighbors or miles apart.
Precisely. This allows grouping based on functional similarity. Those residential areas with similar morning peaks get clustered. The commercial areas with similar afternoon peaks get clustered, and so on. It learns these functional roles from the data itself.
Got it. So step 1, use DTW to find regions with similar demand history. Step 2, group them into clusters. Step 3, aggregate the data somehow for each cluster.
Yes, they aggregate the demand information for their regions within each cluster. And then step 4, they apply self-attention to this aggregated cluster-level data.
Ah, so attention operates on the clusters, not just the individual regions.
Right. This explicitly models those higher-level spatial correlations, capturing the functional similarities beyond spatial proximity. It directly addresses that second limitation we talked about. The case study figure 5, shows this nicely. You can see how it groups those little hexagonal regions in the SON map into larger, meaningful clusters based on demand, not just location.
Okay, that makes sense. So spatial differential attention for denoising the fine-grained view, spatial cluster attention for the high-level functional view. That covers the spatial dimension well. Now let's pivot to time. How does ADFormer handle temporal patterns? Do they also exist at multiple levels?
They definitely do. And that's the job of the systemic temporal attention module. Temporal patterns aren't just about what happens in the next 30 minutes versus this 30 minutes. You have the short-term dependencies, yes, but also broader patterns, the consistent shape of a weekday morning rush versus a weekend morning, or even seasonal trends.
And this module aims to capture all of that.
It tries to, using two main components working together. First, there's temporal self-attention, or TSA. This is basically standard self-attention applied across the sequence of time steps in the input. It's good for learning the relationships between nearby time points in the forecast window.
Okay, standard attention for the fine-grained time steps. What's the second part?
The second part is temporal application attention, or TIA. This is the component designed to capture those higher-level temporal patterns. The paper says it uses a learnable matrix as a kind of query. This query learns to probe the temporal sequence and identify aggregated patterns.
Like trying to learn a signature for morning peakness or evening lull?
Something like that, yeah. It learns to recognize these broader temporal structures. It uses other temporal information, like time of day or day of week features that are fed into the model initially, to help derive what they call a restoration matrix. This helps integrate these high-level temporal insights back into the prediction.
That's interesting. So why no differential attention on the time dimension? They used it spatially for denoising.
Good question. The paper actually addresses this in the ablation study section. They found that differential attention seems to be most effective when you have a lot of elements to attend over like the hundreds of spatial regions. In the temporal dimension, your input sequence might only be, say, 12 or 24 time steps long, like looking back 6 or 12 hours. That's a much smaller number.
Ah, fewer things to get noisy about, maybe.
Kind of. They found that for these shorter sequences, the combination of standard temporal self-attention, TSA, and the temporal aggregation attention, TAA, was enough to capture the important temporal patterns effectively. The extra denoising step wasn't necessary or as impactful there.
Okay, that makes sense. Tailoring the technique to where it's most needed. So putting it all together, the ADFormer architecture starts with the input data demand history, plus things like time of day, day of week features, maybe some kind of positional encoding for time, and a learned embedding for each spatial region.
Right, that initial embedding step sets things up.
And then this data flows through a stack of encoder layers. Each layer uses this combination of spatial differential attention for denoise local links, spatial cluster attention for functional group links, and the systemic temporal attention for multi-level time patterns.
Exactly. It's learning to weigh all these different views, denoised local, aggregated functional, fine-grained temporal, aggregated temporal, to build a really comprehensive understanding of what drives command.
That is quite a sophisticated setup. So the big question, with all these innovative pieces, how did it actually perform? Did it work on real data?
It seems so. The paper presents a pretty thorough experimental validation. They used standard benchmark datasets, NYC taxi data, NYC bike sharing data, and also taxi data from Xinyuan, provided by Didi Chuxing. Real world stuff. And they tested it on two tasks. Single-step forecasting, meaning predicting just the very next time interval, like the next 30 minutes.
And multi-step forecasting.
Yeah, predicting further out, like 1 hour, 2 hours, up to 3 hours ahead in their experiments.
And how did they measure success? Lower error is better, right?
Right, they use standard metrics, MAE, mean absolute error, RMSE, root mean squared error, and MAPE, mean absolute percentage error. Basically, different ways of measuring the average difference between the model's prediction and the actual demand that happened. Lower numbers are definitely better.
Okay, moment of truth. What was the headline result?
The headline, looking at their results table, table 1 in your sources, is that ADFormer consistently and quite significantly outperforms the other state-of-the-art models they compared against. This included older methods like some GNN variants, but also other strong, recent attention-based forecasting models. Across the different datasets, different prediction lengths, ADFormer generally had the lowest error scores.
Wow, okay, so a clear win in terms of accuracy.
Seems that way. For example, on the NYC bike data, the improvement over other leading models was quite noticeable, especially for longer prediction horizons.
And the paper directly links this improved performance back to those core ideas we discussed, the denoising and the high-level correlations.
Yes, absolutely. They argue that its ability to capture those comprehensive spatio-temporal pattern, both fine-grained but denoised and aggregated, is why it performs better. The academic ideas translate into measurable accuracy gains.
That's the goal, right? Theory leading to better practice.
And there's another crucial piece for practice: efficiency. The sources also include results on runtime, Table 2. Despite having these complex, multi-level attention mechanisms, ADFormer was actually shown to be faster in both training time and inference time compared to PDFormer, which was one of their strong baseline models.
Faster? How does that work? More complex usually means slower.
It is a bit surprising, but they mention leveraging computational tricks like flash add-in support. Flash attention is a specific algorithm designed to make the underlying attention calculations much faster and use less memory, especially on modern hardware like GPUs.
So smart engineering alongside the novel architecture.
Exactly. It means the model isn't just accurate, it's potentially practical for real-world systems that need forecasts quickly without huge computational cost. That practical value is important.
Definitely. Speed matters a lot in operations. Okay, let's talk about the ablation study. This is always revealing where they take the model apart piece by piece to see what each bit actually does.
Right, the ablation study is critical for validating why the model works. Is every component pulling its weight? The results here, summarized in Figure 4 in your materials, strongly back up ADFormer's design.
So what were the main takeaways when they started removing parts?
Well, first, it confirmed you absolutely need both spatial and temporal modeling. Taking out either one seriously damaged performance. No surprise there, maybe. But interestingly, the relative importance of space versus time seemed to depend heavily on the type of data.
Oh, how so? What mattered more for taxis versus bikes?
The results showed that spatial correlations were indispensable for taxi demand. Removing the spatial modeling components caused a much bigger performance drop for taxi predictions than removing the temporal ones. But for bike demand, it was the opposite. Temporal correlations were found to be pivotal. Removing the temporal modeling hurt bike predictions much more than removing the spatial side.
Wow, that's fascinating. Any idea why that split exists?
The paper suggests, and it makes intuitive sense, that taxi trips often cover longer distances and are maybe more strongly linked to movements between functionally different zones, like business districts to residential areas. So understanding the spatial structure is key. Bike usage, particularly in dense cities, might involve shorter trips, maybe more routine patterns tied to specific times of day, like commutes within a smaller area or lunchtime rides. So the temporal rhythm is more dominant.
That insight alone is valuable, understanding the data itself better.
Totally. The ablation also showed the aggregation parts were crucial. Just looking at fine-grained connections wasn't enough. You need that higher-level view from SCA and TAA. And echoing the previous point, the relative benefit of spatial aggregation versus temporal aggregation also varied. Spatial aggregation seemed more critical for taxis, temporal aggregation for bikes. It lines up.
And the spatial differential attention, the denoising part.
It proved effective, especially for the taxi data where spatial patterns were dominant and where SDA was applied. It gave a measurable boost by cleaning up those spatial signals. Its impact was less pronounced for bikes, again consistent with temporal factors being more key there.
So the ablation study really paints a picture of a well-designed system. Each major component, the spatial models, the temporal models, the aggregation, the denoising, contributes meaningfully and often in ways that seem tailored to the specific characteristics of the mobility data.
Exactly. It's not just complexity for complexity's sake. It's targeted complexity addressing specific identified weaknesses in how we previously modeled this kind of data. Oh, and the parameters data you included, Table 3, adds a bit more evidence for the aggregation idea. It generally showed that using more levels of spatial clustering tended to improve accuracy, particularly for longer-term forecasts. Suggests those broad functional patterns become even more important the further out you try to predict.
Right, and looking back at that case study image, Figure 5 now, after understanding the clustering.
Yeah, you can really see the concept in action. Those groups of regions aren't just random blobs. They represent areas the model learned has similar demand behavior. It visually shows how ADFormer gets past simple adjacency to see functional structure. It's pretty compelling.
Okay, let's try to wrap this up by summarizing the core contributions. Based on everything we've discussed from the sources, what are the main academic takeaways? What did this research really add?
The paper itself lists a few key things. First, obviously, the ADFormer model architecture itself. designed specifically for this kind of complex spatio-temporal forecasting. Second, that novel application of differential attention in this context, specifically for spatial attention denoising. That's a new technique here for cleaning up the connections.
And the aggregation strategies were key too.
Definitely. Third, the unified spatial attention, that combination of the denoise region level view and the aggregated cluster level view based on DTW similarity. That's a core structural innovation. Fourth, the systemic temporal attention mechanism for capturing those multi-level time patterns. Fifth, really, is the way it integrates all of these mechanisms together into one cohesive architecture for a more holistic model of spatial temporal dynamics.
And finally, the proof is in the pudding, demonstrating it actually works.
Right. Sixth is the strong empirical results showing superior accuracy and efficiency compared to existing state-of-the-art methods on real-world tasks. That validation is crucial.
This has been a great deep dive. It really shows how researchers are getting much more sophisticated in modeling these complex city systems. Understanding these kinds of innovations, like an ADFormer, gives you, the listener, a much better sense of the cutting edge. It's not just about more data. It's about smarter ways to find the patterns within the inherent noise and complexity of urban life.
Yeah, it really emphasizes looking beyond just the immediate neighbors or the next time step. It highlights thinking about functional relationships, about aggregation, and about actively filtering out the noise to get to the real predictive signals.
So what does this mean for you? You've heard how models like ADFormer are moving beyond simple connections. They're explicitly designed to denoise interactions and, crucially, to find those hidden higher-level patterns based on how areas function or how time repeats, not just how close things are on a map or in sequence.
And maybe here's a final thought to take away, building on these ideas. If this approach of denoising connections and finding high-level aggregated patterns based on function, not just proximity, works so well for predicting where people need taxis or bikes, where else could this thinking apply? Could similar ideas help us understand other complex spatio-temporal systems better? Maybe climate modeling, where distant weather systems are linked, or how information or even disease spreads through social networks driven by communities or interests, not just physical closeness. Or maybe even untangling complex global supply chains. What other important hidden correlations might we be missing in all sorts of complex data if we only look at the immediate noisy connections and don't actively search for these higher-level functionally driven patterns?
That's a really interesting question to ponder. A lot to think about there. That wraps up our deep dive into the sources you shared on ADFormer. Thanks for joining us.